Here we go. Hello everyone for that fourth workshops already. It's going fast. Second day of the hackathon. I hope everything is going fine. Can I say some hello as well in the chat if I can see as well some known faces? Hello. And yeah, so we are about to kick off that fourth workshops with Ben, talking about Madara again. So it's Madara Day. I know that everybody is excited as well about Madara and learning more about it. Um, so here's Ben from Starkware. So here's your stage, and enjoy the time.
Hey everybody. Yep, thank you for that intro. Like he said, I'm Ben from Starkware, on the exploration team with Abdel and Lucas. I know you guys went over some StarkNet basics with Lucas, and this will kind of build off of that. We're going to be talking more in the proving Cairo execution traces, proving paradigm, and how that relates to Madara, and what we need to do to Madara to basically make it, a full roll up that proves itself to an L1. And I'm not able to see the chat, so I'm not sure if I need to do anything there. I followed the channel and I'm on the Twitch page.
Okay, you might have to, like on the top right, there's like a little thing that you made me to click it to be able to see in the chat.
Okay, so it only works on full screen, which might be a problem.
Oh, yeah. Okay, otherwise, yeah, that's cool. If I see some question here in the chat, I'll just bump it and ask them from there.
Okay, perfect. Yeah, just feel free to interrupt me or stop me wherever you
Perfect.
need.
Let's do that.
Okay. Uh, uh, uh. All right. We're now going to learn how to add Google permissions to share your screen. The most important thing of the hackathon. One sec.
Yeah. Always the first technical issue since the beginning. So first, I think that it was a first 3 streaks. That was unexpected to have like, okay, 3 streaks. Okay, that's cool. You're already back.
Okay, there we
Here
go.
we go.
Everything good? Everything
Yeah,
live?
everything's
Can you hear me? Okay,
perfect.
cool. Now we should be able to see my screen. Okay. So yeah, like I said, we're going to be talking about Madara and proving and data availability. And then how does proving relate to data availability? And then at the end, we're going to open it up to some kind of architectural questions, especially being a hackathon, there's a lot of cool things that you guys can do outside of the proving context that just is, writing our state diff somewhere that is still really cool and I would love to see in the hackathon. Okay, so I know Lucas gave a good overview of StarkNet, just for those who aren't so initiated with the StarkNet ecosystem. I'm going to build on top of that. So this is kind of a platform wide, 1,000-foot view of what StarkNet looks like and how StarkNet operates. So everything in the red is infrastructure and everything in the blue is execution. So we have clients, these are just SDKs. They might be Chrome extensions, something outside of the execution paradigm that's formatting transactions and allowing for a user to sign those transactions, manage a private key, and initiate a transaction with the sequencer. So the sequencer in today's context of StarkNet, the sequencer is just operated by Starkware. And this is just a first in, first out mechanism. There's no MEV, there's no execution reordering of blocks. Now the problem with that, and I'll start with the reason why that's okay. One of the reasons why that's okay is because due to the inherent properties of Starks and Cairo, the execution of StarkNet can't be falsified. There's nothing that we can do as the sequencer to double spend. There's because of the inherent provable nature of Cairo and the StarkNet OS that's written in Cairo, nothing can be faked by the sequencer, even though it's run by us. Now, the thing we could do, which we don't, but the problem is that we could just drop your transaction on the floor. We could effectively censor the transaction as it comes in. So that's one of the main reasons why we need to solve this peer-to-peer layer, this decentralization of the sequencer, that is one of the things that Madara does really well. Okay, so now we have StarkNet. So StarkNet has an OS, as an OS with a bunch of syscalls written in Cairo. Cairo is provable programming language, and then it has a Merkle-Patricia trie that propagates the account states from one block to the next and from one transaction to the next. I think Lucas basically gave you a good overview of that, so I won't go much more into that. But the leg of this that we'll be looking into a lot is the Stark prover. So we have this batch of transactions, this block, and we know that there was execution and state changes that were affected in that block. Well, what the prover does is it says, and again, this is a shared prover, so it's not just a StarkNet specific prover. This also proves systems like other systems written in Cairo, like StarkX. You might have heard of Immutable or DYDX or SoRare. So any of these systems that have Cairo as their base, it basically just proves the execution of that Cairo code via the Stark protocol. And like I mentioned in the community call, each block in this diagram is an entire rabbit hole to itself. And if you want to go dig down into the Stark protocol itself, you're free to do that. There's white papers. We have some good classes, a boot camp, and that goes into that. But I won't be going into it here. But for all intents and purposes, what you need to know is that StarkNet proves its execution via Cairo, via the Stark prover. So the Stark prover then writes its proof to the verifier that sits on L1 written in Solidity. One of the beautiful things about ZK proofs is that you have this asymmetry between a large machine that is the prover that takes a marginal amount of more steps as it's proving the execution and generates a proof. And then this verifier can live in a resource constrained environment like the Ethereum L1 blockchain written in Solidity. So that Stark verifier then verifies the execution of all of that Cairo code, and it builds what's called a fact registry, which we'll get into a little bit more. So the last piece of Stark that makes StarkNet and makes it a validity rollup is these core contracts here. So there's a set of core contracts that the layer 2 interacts with, and it writes its state update to. If we didn't have this last leg in the core contracts, we effectively would not be a full validity rollup, in the sense that you could not recreate the state of the L2 blockchain from L1. So we always write our state updates to L1 via these core contracts. Okay, so the transaction call flow looks like this. Clients submit a transactions to the sequencer. Transactions are included and aggregated into a block. A proof is generated and it's submitted, and a state update is written. Okay. So since we're talking about DA and how DA works and how we need to format our DA in the Madara context, we'll talk about Sharp. And again, Sharp is the shared prover. And one of the things you need to know about Sharp and DA in general is facts. Like I said, the shared prover doesn't only prove the execution of StarkNet, it also proves the execution of any Cairo code. So you can yourself just write a piece of Cairo code and submit that job to be proved to Ethereum L1. So I'm just going to read these verbatim. The prover takes your Cairo program's execution trace and proves that it's valid, and sends that proof to the verifier, again, which is on L1. After verifying the proof, the on-chain verifier writes a fact attesting to the validity of the proof in the fact registry. So there's a fact registry contract here that houses all of these attestations to Cairo program execution. This fact is like a trustless stamp of approval certifying that the Cairo program was computed correctly. Okay. So in this paradigm, this DApp contract here is actually the StarkNet core contracts. But this is showing you that you can operate an entirely different system outside of just StarkNet via the shared prover. Okay, so we are going to look at that. I'm sure everyone on this hackathon call is like me. You can read these words off a slide, but it doesn't make much sense unless we're actually looking at it. Here is a Cairo 0.x program. And I'm not going to do any kind of deep dive on Cairo. We have a lot of good resources on Cairo, but just know that this is a Cairo program. We declare our output built-ins here, and we have just this simple function. And again, this is more resembling of Cairo assembly as we're dealing with registers here. Don't worry too much about the syntax of this if you aren't familiar with Cairo. We have lots of resources that you can go check out afterwards. I'll comment on what's important here. So basically, as we're going through the execution of this code, we step into main and we have an output pointer. Along this output pointer, we allocate into that these values. So the AP is called an allocation pointer. So we allocate 100 and then we increment the pointer. We allocate 200 and we increment the pointer. We allocate 301 and we increment the pointer. Actually, we're going to do 300. And then we return the new value of the output pointer, which is advanced by 3, which is these 3 values. Okay, so the reason I'm showing you this is because this has nothing to do with StarkNet. This is just a Cairo code block. And because Cairo is a provable language, we say that a lot, but what we don't see, or if you haven't interacted with the sharp, is the reason that's powerful is because we're actually proving it from a prover to a verifier that sits on L1. And it allows us to build these amazing systems like StarkNet, or what the eventual evolution of Madara will look like. Okay. So we're going to compile this program. We get this JSON output JSON. We have the bytecode of the execution of that Cairo code, what built-ins we needed, which compiler version we needed. Again, I'm not going to go into this too much, but we do have some good docs around Cairo. Identifiers, the prime number that underlies the cryptographic curve of StarkNet. Okay, so yeah, the question here is, what is a fact? If you do want to just see some information about this code, you can see if we do run, we can see the execution of it as we allocate this 100, 200, and 300. And these are at the end of the trace because that's where the allocation pointers, the output pointer is at the end after we incremented at 3. Okay. Okay, so submit to sharp. This is just Cairo code that we can submit to the sharp, and we will do so. And what are we submitting? We're submitting the DA compiled.json that we compiled in line 4. Okay, this is going to get into the architecture of Sharp a little bit. And again, Sharp is the shared prover. And being a shared prover, yep.
And someone asking in the chat if we can increase a bit the size of the code.
How's that? Or more?
Yeah, yeah, it's fine. Yeah.
What about is the terminal okay, or would they want that?
Yeah, maybe is it better now, guys? OX Efrain says thanks, so I think it's better now.
Okay, great.
Okay, thanks.
Okay, so you see, after we submit to the sharp, you see that we get a job key here, which is a UUID, universally unique ID, and a fact. So real quick, we're going to look at the architecture of the sharp. Okay, so the sharp is a prover. It sits off chain. It verifies to the solidity verifier on chain, and the primitive value of the sharp architecture is a job. And you can think about it in your head kind of like a train station. So since we're not only dealing with kind of this synchronous execution of blocks that is StarkNet, we're actually dealing with all of these different platforms that can come in this async fashion. You can think of it like a train station. So basically we fill up one train with a certain amount of trace cells or Cairo steps. And again, this is all proving Cairo jobs. The two types of jobs are applicative and recursive. I'm not going to get too much into that, but when you hear we have recursive proving, this is the ability of the sharp to to prove a job that is a proof of a Cairo execution. Okay, so we have these jobs, and it waits for a certain amount of steps to be added to the job, and then it batches the jobs in trains, and it says, okay, we're going to go prove this block of Cairo code. When is a train closed? Well, there's either an expiry so that the platform operator has some guarantee that, yes, I'm not going to have to wait weeks for my Cairo job to be proved on chain, or max trace cells. So once a train gets filled up with a certain amount of trace cells, it becomes optimized for us to prove it on chain. We go ahead and close that train and prove it to L1. So this job key then should make a little more sense. It's a scheduler, so I can then go in and say Cairo sharp status of this job. And it is in progress. Okay. So let's look at that second value. That second value is a fact, and it's a long hashed value. But what is the value? So we have fact check here. Okay, so each Cairo program is just a series in this this format here. So DA compiled. We have attributes, built-ins, compiler version, data, which is the assembly of the Cairo code, debug information, hints, identifiers, main scope, prime reference manager, and that's it. So basically, we can just hash this program. This represents this Cairo code block, and we can get a deterministic hash of this program. If I change one letter, one variable name, if I change anything, I'm going to get a completely different program hash from the one we did previously. So we will hash the program. And we get this. This is the hash of the program. So then what is the fact? Okay. You notice that in the allocation pointer and the output pointer, I was allocating different values into the output pointer. So 100, 200, and 300, and then I incremented the output pointer by 3. So the output of this program is essentially 100, 200, 300 in an array like this. So in order for us to fully represent this fact registry pattern, on Ethereum, we understand it as uint256 in a call data array, which is just because this is the ABI and encoding that Ethereum speaks. So uint256, we'll use the Web3 library to get a hash of that. And again, the hash that we're using is a Ketchak because that is the hash of Ethereum. And we'll do some more encoding as far as the ABI goes. So this is this output value is a uint256 array, and then the fact is a uint256 and bytes 32 Ketchak between the program hash that we got here and the output of the program. Okay, so this is a fact attesting to not only the execution of that code but the output of it. So we'll go ahead and run that. Okay. You see that this fact matches this fact. And I was able to compute it by knowing my program hash and the output of that program. Any questions there? Let's see if that's... Okay, it's still in progress. Okay, so where does this fact registry then live? If you see this, it lives on Ethereum, so we should be able to go query it. Verifier, okay. And I'll send these 2 files out to you guys after, so you can check them out. Okay, so here is the verifier contract on Gurley. So Gurley Etherscan at this contract address. There's this function here that just says is valid, and let's just double check how long we are. Still in progress. Okay. This actually is submitting another fact, but I've already submitted this fact in before, and you'll notice since there's no, like in StarkNet, there is a propagation of some type of block height or block time, so you're never going to get the same fact. Well, this one I've actually submitted before, and there's no concept of time or nonces, so this actually is already valid in this fact registry because I've done it before. But you see that, oh, huh, okay. Maybe I have not done it here before. Okay, that's strange. We're not going to wait for it to go all the way through. It's still in progress. But once this flips, you'll see that this Boolean here is going to be true, and we have a fact attesting to the output and the specific deterministically hashed program. Okay. Any questions yet that I'm missing?
Not so far, not so far.
Okay. Okay, so we'll go back here. So that should give you a bit of a better understanding about the prover. And one thing you'll notice is that, we have StarkNet. Let's go back up to this. We have StarkNet, which is this linear propagation of blocks, and we have Sharp, which is this asynchronous train station that is proving all these Cairo jobs. So the missing link here is this service that's not documented on this page, but it's called the GPS service. And what it does is it queries the Sharp at certain intervals and says, hey, is this job done yet? Are you proved? Is it proved? The reason why we need to know that this is a chicken and egg situation is because we can't write this state diff unless there is a fact corresponding to the state diff in the fact registry. So if we do that, we'll write the state diff here in the core contracts, and we'll say, hey, is there some type of proof that this state update was done? Oh no, then we will stall and we will not write any of that to the core contracts. And then that's what makes us a validity rollup. Okay, so how does this work in the context of Madara then? We have the Sharp sitting outside of any type of context. It's just its own domain. On the left here, we have Madara. The thing that I didn't show you before, and is not well documented, to be honest, is there's a little service in the middle here called the GPS ambassador. What the GPS ambassador does is it takes over that async processing. It says, okay, it basically does that CLI thing I showed you of status update. Is this proved? Is this proved? Is this proved? Can we write a state update? And then eventually, once we can, okay, good, let's write our state update. And not only does it do that, it also submits the Cairo steps to Sharp in the first place. So we have this missing link here in Madara that doesn't currently exist. In Madara today, we run the execution, we get the execution, we understand that the execution is valid, but we aren't proving it anywhere. There's no type of validity rollup context in Madara today, but one that we do want. Okay, so this eventually, and will soon be taken into the client side of Madara, so not the runtime, but the client side, and it will handle this schedule tracking of when we are okay to write to Ethereum 01. Okay, what does that update then look like? So if we go to the call flow, we're specifically looking at 4 here. This is the actual Solidity code for this. So this is the Solidity code in the core contracts for update state. You see that right now, we write our program output you can think about this like 100, 200, 300, except for this is the storage changes of the contracts in the Starknet state. We write it in call data, UN256 call data. So right now, this is fairly expensive. Once we have 4844, we'll be able to write this in blob data, and it will reduce the cost significantly, hopefully. Cool. And again, I'll read this verbatim on the left, and then we can kind of talk about it. Updates the state of Starknet based on a proof of the Starknet OS that the state transition is valid. So again, the Starknet OS is written in Cairo, which means that we can prove the execution of it and get those facts attesting to DA and validity. What are the arguments? Well, we have program output, the main part of the Starknet OS program output, and the data availability fact and encoding of the on-chain data associated with the program output. That should make a lot more sense to you guys now after seeing what just a vanilla Cairo contract looks like. Okay, so we get the state, we get the block number, we validate that the program output, validate the config hash, and then here the state transition fact and on-chain data fact tree encoder. We encode the fact with on-chain data, which is now there because the Sharp has submitted it. And this is again that kind of async workflow that we need the egg before the chicken or the chicken before the egg. I'm not gonna, you guys figure out the philosophy, but one of them before the other. And then log the state transition fact. Cool. So that's literally what the propagation of state looks like for Starknet from L2 to L1. And that is what Madara needs to have if it wants to be a validity rollup. Okay. This is from Blockifier. So one of the questions we have then is, where are we getting this program output, and where are we getting the storage keys that were touched and were updated? So from Blockfire, we have this call info. This is returned from execute. So when we execute a transaction, we get this value of a call info. And at the bottom here, we have storage read values, access storage keys. So this gives us everything in the storage that was updated that we essentially need to write to Ethereum that should have a fact associated with its validity. This is still an open question. There's been some communication in the Telegram today with, I think, some of the folks from Avail. As far as the question of how do we format this state diff, and where in the execution of Madara do we format it to make it most optimized? Some of the options are we can compute the final state diff of the block. So this is what we get from one transaction. So we need to aggregate all of the state diffs, of the transactions in the block. And we could do this on the finalization of the Madara block. The other less defined option is it looks like there are some primitives that are exposed by SC Block Builder, which is a substrate native crate. I have not looked into this yet. I'm mostly focusing on interfacing with the Sharp. So again, if some of you guys on the hackathon want to dig into this, that'd be a great option. This is in the context of today's Starknet. This is not in the context of Madara. But if you're wondering, what does a state diff look like in Starknet today? This is what it looks like. On the left here is what has all of these values collapsed. So it's the block hash. It's the current block hash that's needing to be written to the core contracts. It's the new root that the state update is updating to from the old root, which the state diff is updating from, and then the state diff. So what do we need to know about the execution of Starknet L2 to make it a validity rollup? Well, we need to know what changed in the storage layout of all of the deployed contracts. We need to know the nonces that were updated. We need to know the newly deployed contracts, the old declared contracts, the contracts that were declared in this block, and anything that was replaced. Replaced clashes refers to the migration of the system from Cairo 0.x to Cairo 1.0. Again, slightly out of scope for this today, but just to give you a full breakdown of that. That is everything you need to know about the state of Starknet L2 as it propagates, as it's altered by transactions to recreate that state from L1. So some of these things that are important to blow out. I mean, deployed contracts is just the contract address and the constructor args that were made. So this is really the important one, is the state diffs of the currently deployed contracts. So here at this contract, at this key in the storage layout, it is now this value. At this key in the storage layout is now this value. So each contract in the MPT has a storage layout that's all 0 initialized. And then once, say you have, if you've written Cairo code, you have this syscall called storage read and storage write. Let's say we do a storage write. We will see this come through and propagate in the state diffs. So the key at the corresponding storage layout will be initialized to some value. Anything else I want to say there? Oh, okay, so that's the state diff. Today we need to have something similar as we aggregate the transactions via probably one of these methods here in Madara. Okay, I'm gonna step out of talking about this context, which is the validity rollup context. This is, how do we get Madara to look exactly like StarkNet does today? And I'm gonna start to talk about some kind of greenfield architecture, what can Madara be outside of the validity rollup context? So before we do that, are there any questions?
No question on Twitch so far.
Okay.
Yeah, no question.
Okay. Okay, so this is what might be interesting in the hackathon today. Celestia has a pretty good infographic on this. So if you're looking at Ethereum-centric rollups, the monolith obviously is just Ethereum. So we have execution, settlement, consensus, and data availability, all on Ethereum, and that's just what Ethereum is. A rollup, which is the validity rollup that we have talked about so far. We have execution done on StarkNet, and then settlement, consensus, and data availability all with Ethereum. So we get data availability via the fact registry and via the state update that we looked at today. Validium, Validium, we have this execution done at this higher layer on StarkNet. We get consensus and settlement in a similar fashion that we do on Ethereum today. But then we have this data availability and ability to recreate the state of the blockchain today off-chain. And off-chain can mean a couple different things. Celestia gives us a hint with a Celestium is that, okay, it could just be written to Celestia, or it could be written to Avail. And if we have the fact registry there, we can still get this hybrid version of the world where we have settlement consensus done on Ethereum and our data availability off-chain. I probably should have done a better job of formatting this. But so here on the top left, we have the validity rollup. Top right, we have a sovereign rollup. So you'll see that there's no concept in both of these architectures on the right, sovereign rollup and app chain rollup. We're not really dealing with a sharp. We're not actually, it's not a validity rollup. So we don't have these facts attesting to the state transition of StarkNet. We just need some place to keep our data. We need some place to keep our data and make us a sovereign rollup or an app chain rollup, and that essentially looks like Celestia, Avail, or even 4844 in this blob store. And again, not operating on any context of Sharp. And then on the bottom left, the Validium, this hybrid mechanism where you still are operating with a Sharp, you still have a verifier that's verifying Stark proofs, but most of the data effectively is stored off chain. And you have different data availability guarantees with Celestia than you do Ethereum. So this might be a little cheaper, but a little faster, a little more performant. These are all kind of ideas that you guys are free to pick up and run with. Just writing the state diff and the storage diff to Celestia, effectively making it a. Let me see if I'm getting the sovereign rollup here. If you are familiar with Celestia, that shouldn't be too hard a proposition, and a fun one too, making Madara a sovereign rollup. That is it for me. I think I ended up with about 10 minutes. Any questions?
Any questions? I can't see any questions. But thanks a lot. I felt that the both workshops today on Madara will help so that people kick off building on top of it and build on like exploring. All is fine. Phil says. Yeah, will the slides be available? The recording will be available on YouTube. I may as well contact if people. Oh, if you want to learn more about the challenges as well, I invite you to go to the Teikai platform. I will share the link, and here you can see the descriptive of the bounty of Madara. Let me share it with you directly. So here in the category section on Teikai, you can see here on that link, you can see all the categories, so all the bounties.
Here on that link, you can see all the categories.
Oh yeah. So maybe like will the sites be available? We could make the sites available. I don't know if it's fine with Ben. I will always reach out to other speakers.
Yeah, I'll make the slides available, and I can just send out a tarball of the 2 files that I had demoed today for Sharp as well.
Nice. Perfect. So everything, every content, everything will be available as well. And also like, so on the description of that workshops on YouTube, I will share as well detail of Ben. So if some of the people want to ask questions or have like uncertainties, doubts, you will be able to reach out directly with Ben to ask those questions. So yeah, is there any more questions? Otherwise, I think we're good to wrap up that 4th workshop. Yeah, OX friend saying thanks.
Thanks for having me. Yeah, and feel free to, if you guys are in the Madara Telegram, feel free to ping me, at me, so I make sure to respond. And yeah, thanks for having me.
Thanks a lot. Have a nice day, Ben, and let's continue to hack. Goodbye, people. Bye.